immediately we'll get to the concept of electric field. Okay, so the electric field basically is a force per unit charge, as you know. But what's the big deal? Why is that we want to work with electric fields and not with forces in electricity? What's the reason?
You said you mentioned the sound.
Sorry?
The sound over there.
Oh, yeah, thank you. Sure, let's do that. Yeah, I forgot. Yeah. So what I meant by that, your question was, is that, okay, so with this, so Fij meant the force of I on j for two particles. Fj, on the other hand, now means the total force on j. So the assumption, the picture that I'm going to draw, is that there are 100 I particles acting on j. Okay, so this is the thing. So I have particle 1, particle 2, particle 3, particle 100. Okay, so let's suppose that those numbers can be considered to be an index I that runs from 1 to 100, and then I have my particle j sitting somewhere in there. Okay, so this is the picture that corresponds to that sum, so that you have this force here, 1 on j. This would be 2 and then this is 100 if 100 on j. So you can see that on point j, the force F1 on j, F2 on j, F100 on j, so we add them up. Basically that's what we are doing, because the index I runs from 1 to 100 and j is fixed in this sum.
Superposition principle?
Superposition principle, yes. And it's tested experimentally. At least for this type of problems it works. Okay, for this type of electric problems it works fine. Okay, so one of the reasons why we introduced the concept of electric field is because so at the end of the day, when we do something, some mathematics in a physics context, is because we are thinking, hopefully, at least in the back of our minds, that there is some experiment that we can eventually do, some measurement that is related with reality. And so at least one of the problems with working with forces is that if you have 100 particles, and you wanted to answer the electric field?
Yeah, the magnetism is interesting, easier because you have the force at any point for each particular particle. Meaning if you make a plot of what all the particles are and you're pointing to the center, so you'll know, based on the field equation, what the force is on each one of those particles.
Oh, okay, yeah. Mm-hmm.
Makes it simpler.
Yeah, that exactly. It makes it simpler for sure. Mm-hmm. Yeah. Okay, so that's actually one of the reasons. So let's think about this first in this way. Let's suppose that we have 100 particles, yes, that are just floating around, and let's say that they're in equilibrium. Okay. Now it turns out there is a theorem that shows that electric particles cannot be in equilibrium simply by electric forces. Okay, you cannot arrange a bunch of particles, positive or negative, so that they will be in equilibrium. Okay. So, for example, if you have a positive and a negative charge, only with those forces they will attract each other until they collide. If they are both positive, they will repel, okay, and they will go to infinity. Okay, so those are simple examples of what I'm saying. You cannot, if you have 3 particles, there is not going to be a way to organize them so that they are in equilibrium. Okay, but electric charges in equilibrium do exist, but only because there are other things that hold them in addition to the electric forces. Okay, so for example, a typical example is that you get a chunk of metal and you charge it with 1 coulomb. That's a possibility. And the charges are there, maybe somehow macroscopically they are not moving. So how is it possible? Well, it's possible because each particle is in a combination of the other particles, the other charged particles there, but also there are walls in the material that prevent them from going away, okay? And the origin of those wall forces we don't need to talk about now, but they exist. So anytime that we have confined electric charges is because in addition to the electric forces, there are other forces that keep them together, okay? If not, it's not possible. All right, so the example of a metal is very nice to see why, one of the reasons why electric fields are interesting. So let's say that I have a bunch of charges inside a conductor, okay? And we will learn later in more detail, but conductors can very easily move charges around, okay? And so if I have a charge, a metal that is charged, there are charges in there, and now I'm interested with an additional charge from the outside to measure what force acts on that additional charge. Okay, so in other words, just to simplify the talk, I have 100 charges inside the conductor, and I bring the next one, 101, outside of the conductor, and I want to know what force acts on that particular charge. Okay? And now the problem is that when I bring that new charge into the neighborhood of the conductor, because the charges, or many of the charges in the conductor are very free to move, very easily movable. So if I bring a charge close to the conductor, I'm going to move the charges in the conductor, and that's a fact. And so the force that I'm going to measure is not really the force I wanted to measure, because by bringing a charge close to the metal, I'm moving the charges that I want to measure. Clear? Okay? So the picture would be something like this. I have a conductor here, and I have charges, okay, positive charges in there. And now I bring, say, a positive charge close by, and these charges that are there, they can move freely, they will be pulled back. So I'm going to end up with a picture like this instead. This would be initially when this charge was very far away, and when I bring it closer, I'm going to have a much larger positive charge here, because this region was depleted, and this is going to be negative. Okay, in a real material, in reality, what happens is that the electrons that exist, that are the real movable ones, are going to move closer to the positive charge. Okay, and I'm going to end up. So the problem is that if I have this situation and I wonder what force would my particle feel here, and I bring it to measure it, I get the wrong answer because I'm measuring something else. Is that clear?
No.
No, okay. So I have an object that this conductor is charged, and it has a distribution of charges in there. Okay? So I say, okay, so I'm very interested to put something to an engine, a machine there. So I want to know what the force is of this thing. So now I grab a particle, a positive particle, to measure that force according to Coulomb's law. Now I bring it in and I change it. So that's a big problem because I'm not measuring what I want. So that's when one of the reasons why the electric field becomes very important. The one, okay? So first of all, to do this experiment, what we need to do is we can do this thing, yes, no problem. But this charge should be very, 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 very tiny. So tiny that this is not perturbed. And that, okay, so how do we know that something is tiny? Well, okay, so it depends on the situation. If we are dealing with charges that vary in our experiment within maybe 1/10 of a coulomb, that's important for us. then we can just pick up a charge that is 1 millionth of a coulomb, 1,000th of a 1/10,000th of a coulomb, and then it's not going to affect our system, okay? But that's just a practical thing. But theoretically, all we require is that we measure a force in general, in any situation, with a very tiny particle. That is basically the first step to define the electric field. So the electric field is defined as the force per unit charge, but when that charge is infinitesimally small, okay? And so many times it won't matter, but the strict definition is that, okay? So we take at location R, we are interested in defining that electric field, and we do it as the limit when some charge, which we call it a test charge, is very small, and what we do is we use that test charge Q to measure the force at that location and divide by the value of the charge. Okay? So what justifies that sort of thing? Well, you see, because of the superposition principle here that we had before, the force acting on particle J by a bunch of particles i's is a sum in the index I that depends on the location of particle J, of course, but the magnitude of the charge J pulls out from the sum. So it's very easy from this thing to say that the quantity Fj over Qj doesn't depend on the charge. You see that? Doesn't depend on the charge mathematically, of course, as long as all the charges Qi are located at Ri. But if my charge Qj is too big and moves everything around, it's a different story. Okay? But that's why in the definition we need a small charge. Yeah?
I'm so confused why these different having test charges, because maybe everything's wrong, but would it be the flux is the same no matter how intense the test charge is? Because the spheres or the object still encloses the same amount of charge, no matter if the charge is distributed. So no, but that's a difference. The flux is one thing, but we are just talking about forces here. Just very simple forces. No, you see that's one thing that we are going to clarify soon, because one of the problems is that if you go back to your book in freshman physics, the second semester, then or third, now you are doing it now, I think a little bit of that, right? With Quidditch, you're doing, yeah. So the thing is, the chapter in Gauss's law emphasizes that Gauss's law is used to obtain electric fields. But this is sort of conceptually not that good, because it is true in some situations with very high symmetry that you can do that, but in general Gauss's law is not useful to find electric fields, because if you have a sphere, if you have a cylinder, fine, then you can actually, but let's suppose that I have a very horrible distribution of charges. I can still use Gauss's law, but I won't be able to find the field, because any surface that I take, the electric field is going to be non-uniform on that surface. And so those problems with high symmetry require that the field, the magnitude is the same on all those points for you to be able to obtain that. So the fact that the flux gives you information doesn't mean that you can actually obtain the electric field or that it will be the same. I'm considering a very general configuration of charges, and so clearly there's going to be a flux, but I can say nothing about the electric field of the force. So that's why I'm going straight to the basic concept of force and electric field, and realize that if I have a very large charge, I may affect my system. That's all I'm saying. You know? Okay. Okay.
Are you? How exactly does that work where the limited Q goes, the charge goes to zero? Because then your force at that location
also goes to zero. Yeah, but you don't stop, you know.
Meaning it's a small charge. But I just gave you an example. You see, if you have a system that, because of the details of the system, whatever, that you won't perceive a change in the position of the particles. Let's suppose that you are measuring with a ruler that has certain precision, okay, maybe a millimeter. And okay, so for you to move any of the particles 1 millimeter, you need a certain force on that particle. So it turns out that if I bring a particle Q that is a microcoulomb, I cannot detect any displacement within a millimeter, then I'm fine. But I cannot define the problem better without going to the lab. This is just conceptual. So I need to deal with what I'm measuring to tell you more. All that means is a very small quantity.
So
okay?
Practically, are they, I'm assuming, very accurate today? Like to measure the...
Depends on your experiment. That we cannot say anything at this stage. But the limit is very valid, this ratio, simply because I was trying to justify that because of this. Because the ratio of the magnitude of the force to the charge is something that is, has a value. So the limit is correct. In other words, what it means really is the following. It depends on the accuracy, so this is a little bit spending too much time on a detail, but once I find that my charge Q is small, that doesn't move my system, what that's telling me is that if instead of using 1 microcoulomb, I use 1 nanocoulomb, I will still get the same electric field, but only that the force will be reduced by a factor of 1,000 also. That's what the ratio will remain the same. That's what it means. But first I need to get to a small value of Q. Okay? All right. So we have that. All right. So now according to that definition and using the superposition principle plus Coulomb, is now very easy for us to write what the electric field would be at location J. Yes?
What we wrote over there for the electric field, would that just be the magnitude of the field at a certain point?